This is a CHEM Study film, a production of the Chemical Education Material Study. From naturally occurring sources of carbon, such as oil, or natural gas or coal, chemists have learned to make countless new organic compounds. The preparation of a desired chemical compound from another known substance is called synthesis. We are going to demonstrate a typical synthetic operation. 2-butanol, an alcohol, will be transformed into 2-butanone, a ketone. The key reaction in the synthesis is the oxidation of an alcohol functional group into a carbonyl group. The carbon skeleton remains the same, with only the functional group changing. Sodium dichromate will be used to oxidize the alcohol. In the reaction, the orange dichromate ion is reduced to green tripositive chromic ion. In this reaction flask, the synthesis takes place. The alcohol will be oxidized to a ketone. This distillation equipment is used in the purification of the ketone. The identification of the ketone is done by infrared spectroscopy and also by forming a solid substance whose melting point is determined. Synthesis, purification, identification, key steps in making any new organic compound. To prepare for the synthesis, the apparatus and the reagents are assembled. But how much of each reagent will be needed?
To find out, we first write a balanced equation for the reaction. This is the way we do it. We start with the structural formula for 2-butanol. The products of the oxidation are the ketone, plus 2 hydrogen ions, plus 2 electrons. This is the half reaction for the oxidation of the alcohol. The oxidizing agent is dichromate ion. The dichromate ion is reduced in the reaction and forms tripositive chromic ion plus water. In order to balance this half reaction, we need 14 hydrogen ions and 6 electrons. These two half reactions involve 6 electrons in one reaction and 2 electrons in the other. To make the equations equivalent in the number of electrons used, the top equation is multiplied by 3. Adding the half reactions, we get the equation for the net reaction. Butanol is oxidized to butanone, and dichromate in the presence of acid is reduced to chromic ion. With this, we can calculate the amounts of reagents that will be needed. 2-butanol has this structure and a molecular weight of 74. For the size of the apparatus we shall be using, 1/2 mole of butanol will be a convenient amount. Let's base our calculations on that amount. 1/2 mole, then, will be half of 74, or 37 grams.
First, the empty beaker is weighed. and the balance set for the 37 grams determined by the calculation. Next, the amount of sodium dichromate that will be needed is calculated. The required amount is then measured out. Sulfuric acid, the source of hydrogen ions, is also weighed out in the amount required by the equation. In this way, the amounts of the three reagents that are needed in the synthesis are determined and weighed out. Now the sulfuric acid is diluted with water. This must be done carefully by pouring the acid into the water while stirring constantly. Note that the heat of reaction vaporizes water, which condenses on the side of the beaker. To the sulfuric acid and water, the sodium dichromate is added. This gives an aqueous solution of the oxidizing agent in the form in which it is used in the reaction. Diethyl ether is used to dissolve the butanol. The amount of ether added to the butanol is not critical because it is not consumed in the reaction. Rather, the ether dilutes the reaction mixture so that the rate of reaction can be more readily controlled. Also, the ether's solvent properties will be helpful in the purification of the product. After the solution of butanol in ether is poured into the reaction flask, the oxidizing solution, made from sodium dichromate, sulfuric acid, and water, is placed in the dropping funnel. Ether and water do not dissolve in one another. However, vigorous stirring assures that the two solutions will be in contact so reaction can occur. The dichromate solution is added to the flask at a controlled rate. During the oxidation, heat is released. This is absorbed by the water bath surrounding the reaction flask. As the reaction nears completion, the orange dichromate ion has been reduced to green chromic ion. The actual synthesis is now completed. The flask contains the ketone, plus some inorganic materials, and the solvents that were used. How is the ketone purified from this reaction mixture? The first step in the purification of the ketone is to place the reaction mixture in a separatory funnel. The ether and substances soluble in it gather in an upper layer, which will become more visible as the purification continues. Water and substances soluble in it settle into a lower layer. After settling is complete, the lower aqueous layer, containing most of the inorganic materials, is drawn off. The remaining ether solution, containing most of the ketone, is transferred from the funnel into a clean flask and set aside. The aqueous layer is returned to the funnel. A further portion of fresh ether is added to extract any ketone dissolved in the water. The ether forms a layer on top of the aqueous layer. Vigorous shaking mixes the layers. Opening the stopcock from time to time relieves the pressure due to ether vapor. When the layers have separated, the aqueous layer is again drawn off. After several such extractions, almost no ketone remains in the aqueous layer, which is then discarded. All of the ether extracts are now returned to the funnel. The ketone obtained in the synthesis is in this ether solution. In addition to the ketone, this solution contains ether, traces of the sulfuric acid, and some of the inorganic materials used in the synthesis. Addition of an aqueous solution of sodium hydrogen carbonate neutralizes the sulfuric acid. The reaction of the bicarbonate with sulfuric acid results in the formation of carbon dioxide. The pressure of this gas is relieved during the washing operation. The layers are again separated. Distilled water is now added and thoroughly mixed. Repeated washings of this kind remove any traces of inorganic ions and yield a nearly clear liquid. After the final water wash is withdrawn, the remaining ether solution still contains traces of water from the washing operations, as the cloudiness indicates. Anhydrous sodium sulfate is added to the ether solution and absorbs these traces of water. A clear, dry solution of ether and ketone remains, which will be separated by distillation. The ether solution is removed from the drying agent by filtration into a distillation flask. Small boiling chips of a porous material are added because they promote the formation of bubbles and ensure smooth boiling. Because ether is being distilled, the risk of fire is reduced by using an electrical heater under the flask. In a short time, the solution begins to boil. The boiling point of ether is 35 degrees. The ether vapors condense in a water-cooled coil and collect in this receiver. Eventually, the temperature starts to rise above 35 degrees. This is an indication that most of the ether has been distilled. The material remaining in the distillation flask is the ketone plus residual ether. It is transferred to a smaller apparatus to minimize loss of material during the final distillation. The boiling point of the ketone is listed in the handbook as 79.6 degrees. However, when the temperature reaches 35 degrees, the first material coming off will be the residual ether. As distillation continues, a ring of condensing ketone vapor rises through the column and surrounds the thermometer bulb. The temperature increases rapidly. At this point, the receiver is changed and a previously weighed flask attached. The temperature soon becomes constant just below 80 degrees. This indicates that our purified ketone is distilling and collecting in the receiver. The flask is weighed to determine how much ketone has been obtained in the synthesis.
The actual yield of our ketone is 30 grams. What is the maximum amount of ketone we can obtain starting with 37 grams of the alcohol? Let's see. The oxidation of 1 mole of alcohol, 74 grams, will yield 1 mole of ketone, 72 grams. Therefore, 37 grams of alcohol could have given a maximum of 36 grams of ketone. The amount of ketone we actually obtained was 30 grams. The result of a preparative experiment is usually reported as a percentage yield. The actual yield, 30 grams, divided by the theoretical yield of 36 grams, gives us 83%, the percentage yield. This is a reasonably good result. Yields as good as or better than this can often be obtained if one is careful in controlling the conditions of the reaction and in isolating and purifying the product.
How is the identity of the purified product confirmed? Here is a frequently used test. Dinitrophenylhydrazine in alcoholic solution is allowed to react with the ketone. The product of the reaction, which crystallizes from the solution, is called a derivative of the ketone. The crystals of the derivative are collected by filtration. After drying, they are transferred to a watch glass, and a sample of the crystals is manipulated into a glass capillary tube. The tube is inverted and the crystal shaken into its sealed tip. The capillary is placed on a thermometer and inserted into a heating bath. The bath is slowly heated. As the temperature rises, the crystals are watched closely. The exact point at which the material melts is noted. There. 111 degrees. This temperature is called the melting point and is compared with the recorded melting points for such derivatives. Agreement between the observed melting point and the recorded value identifies the product as 2-butanone. Here is another identification procedure. A known sample of the ketone is poured into a small container and then into a cell which fits onto the infrared spectrometer. The infrared absorption spectrum is measured on this instrument. The spectrum of the known sample of the ketone is compared to the spectrum obtained from the product of our synthesis. Since the curves match, the two materials are the same and the previous identification is confirmed.
synthesis, purification, identification. These are the key steps which you have just seen in our synthesis of 2-butanone. This preparation of a ketone from an alcohol shows some of the manipulations performed by the organic chemist in synthesizing new compounds for scientific study and practical application.